Okay, I'm going to begin. Let me share the screen. And I am excited to talk about this topic today with you. This is a new diagnostic that we'll talk about. It's not new, but it's a new for this course diagnostic that we will talk about. And actually, this is from, so this is from a conference that I was asked to give a talk on this metrology last year, but it's actually perfectly geared for this class because the session at that seminar was an educational session for practicing engineers, because the Society of Experimental Mechanics discovers over the years that you have legions of people coming through who aren't as up to speed, especially students aren't up to speed, grad students say are not as up to speed on these techniques. And so they create special sessions to try to provide half-hour concentrated tutorials on these metrologies. So I was asked to do one on interferometry last year, and it was very much based on course notes that I had developed in 50. I just decided to refine it for that conference. So pay no attention to the title. It could literally just be called ME50 Lecture 12, okay? But I have actually tweaked it a little bit for that audience, and I may go back and forth to my older slides as we go. Now, I'm gonna, okay, guys, I need your attention. Thanks, okay. This tool right here is a base model that Polytech offers. The goal of a lecture like this would be to have you understand what's going on inside that box. That box shoots a laser beam out to a surface of interest and probes its motion. It could be any vibrating structure, and it receives that reflected laser light. And somehow, right now, it just looks like the proverbial black box to us, right? Somehow it takes that received light, does something with that laser light, and reports back to us signals that look like what I had on my title page, or better yet, signals like this. So this was a demonstration in our lab, and you can see that beam vibrating, and that's the admet, which I simply used to clamp the beam, okay? Because try clamping a beam, easier said than done. You think get a C-clamp, right? It's terrible. The edge of the table is moving, right? You want a real true rigid clamp, you've got to find a structure that will allow you to really hold that thing down. So I just decided to put it in compression. Now you see the zoom in, and you see that little red dot of light, that focused light, and you see a strain gauge right next to it. So the laser is pointing straight down on the beam, okay? So this is the laser vibrometer shooting a beam straight down, reflecting laser light. And then as that beam vibrates, laser light is brought back to that device. And, well, there's a nice blow up. Okay, there's a strain gauge, but just ahead of the strain gauge, you see that retroreflective tape that I've taped down. It just promotes reflection. It promotes the scattered light to come back more efficiently. And so we had both strain gauges and the laser vibrometer producing these ringing curves that you see here, okay? So we would literally flick the beam, let it ring, and then its oscillation and its dominant frequencies would drive that signal, and then it would subsequently decay due to damping. And so what you see are just multiple attempts at us just flicking the beam. So those multiple repeated blue curves are just us flicking the beam, having it die out, letting the device continue to collect data, flick it again. And then the magic is really in the FFT, which I'll talk about more in depth later on. But in that lower right, where you can do an FFT analysis of the very signal you've just collected, and out will come these peaks, which seems to sort of emerge from all of this heavy muck. All of a sudden, boom, out comes this spike, okay? And then more of this stuff, and then boom, out comes this spike, and boom. And these are the dominant frequencies that are present in that vibrating structure, okay? This is a big business in the mechanical engineering world. The vibration of structures is a pretty big deal, especially when you're worried about, say, a device surviving liftoff and transport into orbit. Okay, people put every device that's going to go up to the space station, or better yet, to the moon eventually, through a lot of vibration testing to make sure that that device has the integrity to survive the vibrations associated with launch. And there are many other cases where you could think about where vibrations matter in the transportation of anything, even terrestrially, right? So this module and any demonstrations that I get to do with you will involve trying to communicate to you the big picture of how this thing is done. You try to model it, and you'll have a modeling assignment where you'll model vibrations, okay, both torsional and lateral. And you'll have ANSYS predict what the vibrational frequency of that beam should be, or the mode should be. And then it's fun to go in the lab and see some of those very things through measurement, okay? Now, I could have just as easily not shown you this vibration equipment and told you that that strain gauge on the beam reported to us vibrating strain signal, right? So even though we've been using it in the static sense so far, where we've been deflecting a cantilever, or I've been asking you to imagine how it works, the strain gauge is an absolutely dynamic sensor. And you could simply say, hey, give me the epsilon 1 component, or the 2, or whatever grid strain you want to report. And instead of concerning yourselves with the strain analysis and the Rosette analysis, you could just say, I'm just going to use that strain signal as a metric, and I'm going to extract frequency data from it. So this could have easily been grid 1 on the beam of a Rosette grid. Now, this happens to have come from the vibrometer, but that's the beauty of this, is that there are many, many ways to draw the frequency information from the structure, okay? You glue a strain gauge to it, and as long as your data acquisition equipment is fast enough, it'll keep up with those oscillations. It'll report to you whatever the vibrations that the strain signal picked up. And actually, strain gauges turn out to be an excellent way, as we'll see. The vibrometer is exquisite, though. It has a higher fidelity. It has a finer resolution. And what you're seeing here are way out here are higher modes that are super weak in reality, okay? The dominant mode is probably this mode, right? This flexure mode that you see and you imagine with your eye, but superimposed on it are these other modes of much smaller amplitude, but they have the S shape and other shapes. And this is a log plot of the energy spectrum. So to draw these out, you have to use a log-based plotting curve, and then out are coming some of these higher order modes that are present, okay? So this is more of an introduction, okay? But let's keep thinking about the device itself. So I draw that black square just because I'm kind of blocking what's inside the laser box momentarily, and I'm saying the only way you can truly appreciate how this laser vibrometer works is you have to go and talk about the optics, okay? And it's actually quite interesting. You say, how is it that we can, again, send this light beam, this laser light beam at a surface, collect it, and somehow come away with this vibrometer? The answer, in part, and we'll get to the final answer, but you'll have to wait for it, okay? And I may have to take 2 lectures to get through this, because if I rush through it, I think it just loses the entire effect. The magic of any laser interference tool is in the combining of 2 beams of light. And so I want you to imagine, we haven't seen all the details yet of where these beams have come from, but I want you to imagine 2 laser beams, one of which we will give a name. We'll say this is the reference laser beam, and these dashed lines just sort of represent its diameter, okay, as it approaches this beam splitter. How many have been in an optics lab before and seen a beam splitter? You've seen one before, okay? It's a beautiful thing. It's 2 cemented glass prisms. It's 2 cemented glass prisms. It's a block, actually, okay? It looks like that, okay? And this coating is very precisely prepared to transmit about 50% of the beam. And this one will reflect about 50% of the light that comes in. So it's a splitter. And you can arrange these coatings to do various things, 50, 70, 30, 80, 20. The most common is a 50-50. That's a beam splitter right here, okay? And so here comes this reference beam that we've derived from our laser, and it comes to the beam splitter. What does it do? It splits in half. Half goes this way, half goes that way, okay? This beam we call the test beam. It came from the surface of interest. It came from our vibrating cantilever beam. It came from something that's moving and vibrating, okay? And it carries with it optical information associated with that motion. And that beam is called a test beam, and it heads to the same beam splitter, okay? And it splits. And if we're careful in our ability to align this optic, we can superimpose these beams beautifully on top of each other, okay? So upon reflecting, we can, with the right degrees of freedom and appropriate optical controls and stages, you can do this in a laboratory as a demonstration. You don't have to buy a $100,000 device. You can buy optics and do this on an optics table. You can mix these two beams so that they're beautifully collinear and concentric, okay? So out comes these two beautiful collinear and concentric beams, okay, which are traveling in space, okay, and they're right on top of each other, okay? The magic of interferometry is what happens when you do that. And one of those beams came from a moving source, and the other one didn't. In this case, it just came from the laser itself, okay? The magic to appreciating why these two things beat, these things are going to beat, literally. If you put a photo detector here, and this surface is really moving down here that reflects this beam, these two are going to go and interfere and beat in a way that the intensity of light is going from a maximum to a minimum, and the photo receiver here would report that to an oscilloscope, okay, as an analog fluctuating signal, okay? So that's the magic of interferometry. Now, again, these are just words and very, very simple, basic diagrams. We have to keep peeling the onion to finally get to some mathematics that says, what do you mean beating? Why would they beat at all? What is it about that signal? Okay, so I'll tell you a few more things before we move on. So these vectors K, these are the wave propagation vector. They basically say the beam is moving that way, and K, if there's a wave front to this laser beam, K is normal to it. We see this K a lot in mathematics classes, okay? It's actually the wave number 2 pi over lambda, but it has a vector to it, okay? Okay, it has a vector to it, okay? So notice each of these has a K, right? And then there's something else that I've drawn on here, and that's those little red arrows, okay? And they remind us that a light beam is really an electromagnetic field. And the electric field, which is really the manifestation of this light beam, has a transverse vibration perpendicular to the direction the beam is traveling in. So when laser beams traverse, the E field is like this, okay? And the beam is going that way, but the oscillation is transverse. And so we draw and we write the electric fields of each beam in that way, okay? Such that when they meet, okay, now they combine. And you really are getting E1 plus E2. Note the vector that I'm putting up above them, okay? So the photodetector or the camera sees the effect of E1 plus E2 superimposed on each other. What is totally not obvious right now is why would those beat? Why would the photodiode suddenly start reporting this? Okay, why? Why does it suddenly start reporting out an electrical signal that has frequencies to it? Okay. And that's the motivation behind digging into this and not just accepting it and not just saying, oh, okay, thanks, now I know what it does. Okay, let's keep peeling it and thinking a little bit more about it. So you have to do a slow digression just to understand how light beams are modeled. If you can't stomach that, then you can't possibly know, okay? And there's no one in this room that doesn't understand what this is mathematically, at least. This literally is e to the I, yes, that I, right? K is that propagation vector that I just talked about, okay? Dot R means dotting into a position in space that it is heading toward, okay? So you have to dot K and R in the phase. This is called the phase portion of this signal. And then minus omega. Omega is the light oscillation. 2 pi f of the light field. This number is super ridiculously high, on the order of 10 to the 14 hertz. Okay, light is oscillating at frequencies like 10 to the 14 hertz. So, you know, this is that omega. This is the omega of light, of your laser light. This is time, t. So we write it this way using complex notation. You could write it as cosine or a sine, but writing it this way, as you'll find out, is a much more effective way. This is nothing but the amplitude of the electric field, E naught, outside. So just to summarize, you could imagine that this is the planar wavefront of the laser beam that's propagating in your interferometer. And since everything's going in one direction, K dot R just becomes K dot X, and you're just propagating in a straight line, okay? And minus omega t is something that keeps track of time. And this out front is nothing but the amplitude of the light field. Okay, so back to this, each of these beams that we're sending in, say the test beam from our surface or the reference beam, each has a representation like this. Okay, and this is a very, very reasonable way to model a light beam. Laser beams, strictly speaking, aren't perfect plane waves. If you really look up laser beams, you'll find out they're Gaussian intensity profiles traveling through space. Okay, so laser beams really have intensity that does that. Okay, it's a Gaussian. But when we expand them, we flatten that Gaussian an awful lot. And this model of a plane wave of constant amplitude is sufficient for the purposes of finding out what the interferometer does. Okay, so that's an ingredient for what I'm trying to cook here today with you. Okay, this ingredient is how you model the electric field of a propagating light beam. Okay, now, well, let's just move on. Okay, it's an ingredient. Now I have to tell you about another very important ingredient. Let me talk about what is called optical phase. Looks complicated, but I'm going to give you a very practical definition in 2 seconds. What it says is all objects, all transparent materials, air, glass, have an index of refraction. That's what n is. Okay. And when a light beam is traveling through a distance, ds, the optical path is called index times distance. In air, the index is something like this. The index of air is something like 1.003 for air. So nobody speaks about that 3, okay? Everybody says the index of air is 1, okay? For all intents and purposes, it is. Vacuum is 1, right? Okay, glass, it could be like 1.5. Water, it could be like 1.3, okay? So this index has something to do with the wave speed of light in that medium. Optical phase is nothing but 2 pi over the wavelength of the light times the distance it travels, okay? And if the index is not 1, then an index n would have to sit in here, okay? So in a vacuum, you notice I'm saying in vacuum, it's because n equals 1, the optical phase is 2 pi over lambda times the distance it went from S to P. It's as simple as that, okay? The integral is just saying, in general, if you had some wild n that actually varied in the material, then you'd have to do this integral to actually get the phase, okay? But that's exotic. That does happen. People who study, optics on a very high level do study very exotic properties and principles, and they may have a graded index of some kind. And then, yeah, phase is computed this way. But in the real world, this cube beam splitter has one n, okay, one index. N equals 1.52 maybe. Okay, that's it. Okay, it's isotropic. Okay, so optical phase is nothing but 2 pi over lambda naught. Lambda naught is the wavelength of the laser light. Okay, you should think of that, right? So this laser light beam has, it might be, if it's red, if it's a helium neon laser, it would be 632.8 nanometer wavelength, a nice red laser beam. Helium neon, okay? Hini, as they're often called, okay? Hini laser, okay? There's other very, very famous wavelengths. There's another one that you buy commercially, very common. 532 nanometer. It's a green laser. Okay. Lasers come in all kinds of forms. Okay, but certain ones have sort of become very popular because they generate very energetic beams, very stable beams, and they've been commercialized and sold. Okay, but let's show you the rest of this little phase. This is a little phase digression. So you have to get a feel for what phase is in optics to understand what an interferometer does. Let me cut to the chase and tell you. The interferometer is responding to phase differences. Okay, so if I convince you what phase means, then you'll understand eventually why, when we mix these two beams, there's a phase difference between the one that came from the specimen, the vibrating beam surface, and the one that didn't. And the interferometer is responding to those phase changes. So this is why I have to digress into phase. So let's talk about that. So let's consider this thought experiment. Okay, so this is a vacuum. Okay, and let's not concern ourselves with how we would do this. Okay, but this is a distance from S to P, and there's a length L in the vacuum. So we'd say, okay, the phase is 2 pi over lambda naught L. Okay, and then you say, okay, what if I just suddenly insert a glass plate in between S and P? Okay, I'm just going to insert this yellow block rectangle, which represents my glass plate. And I say, what's the phase now associated with this path? Well, now I have to carefully add. The index was 1 from here to here. Then it was 1.5 or whatever the glass is from here to here. And then it was 1 again from here to here. So if you then say, after inserting this glass plate, okay, very carefully, let me just open up the whole slide and show you what happens. Okay, you say, here's the OPL, the optical path length, with the glass plate inserted. Okay, notice it's this distance x1 from here to here in vacuum, plus, note the presence of the n, plus n naught times the thickness of the glass to accommodate for it traveling from there to there, right? Plus x2, which is from there to there, right? Okay, so then you say, okay, how does that differ from what happened before when it just went L the whole way, right? Well, L, I'll remind you, L is nothing but x1, nh, and x2 before we stuck the glass plate in, right? Okay, so if that's true and you say, what's the difference between no glass plate and glass plate, then you subtract the two, okay? You subtract the two, and you say one minus the other, and I'm left with this, okay? All right. So if somebody said, what's the change in optical path length that just happened when you inserted that glass plate, you'd say the change in optical path length was this, because I had to subtract the OPL with the plate minus the OPL without it. Okay, makes sense? And then you say, okay, now give me the phase of that. That's why I've done this in 2 parts. This is just the path length. Now you just multiply it by 2 pi over lambda naught. See? And notice what happens here. The length unit cancels, right? This is a distance, h, divided by the wavelength of the light, and you just get a number in radians here. See? So phase is just some number in radians, okay? And the optical path length is a physical path length. So to continue this thought experiment, if I did have some kind of a sensor back here the whole time that was receiving this beam, and it somehow was sensitive to phase, as soon as I inserted that glass plate, it would have reported that change, you see? And that change in phase would have been this much, okay? So this is a very simple way of introducing what phase is. Now, let me show you what it looks like when we decide, okay, to keep this thought experiment going. Let me just open up the slide, okay? So now imagine this with me, okay, since you've come this far. What if, and just hang on to this question of like why or how this would happen, but what if this glass plate could change thickness suddenly, okay? That's what this DH is about. Why am I getting at this? Because in mechanics, things change shape, right? In mechanics, things change dimension because we strain them, right? So imagine if this glass plate could strain and change its length, and we're still in this thought experiment, then we'd say, whoa, we have this other thing that could change phase now. It wasn't just inserting it anymore. It actually, H grew a little bit, the thickness grew. And so you say, oh, I now have to consider the effect of thickness change as well, okay? And when you do that, okay, you say, well, there it is. There's the DH, okay? There's the DH from the previous formula that we derived, okay? So you realize now that the previous case, all I did, just to back up, all I did in the previous slide was insert a glass plate, right? And we got that the phase was 2h times n naught minus 1 scaled by this factor. And now I'm saying, what if we perturbed h? Then this would become a DH, boom, okay? And you'd see that change as well. Now, another thing that could conceivably happen, I'm not saying it always does, but the index could suddenly change. Maybe the index of refraction of this thing that you've just stressed changes upon being stressed, okay? If that happens, then you have that possibility, okay? Okay, H is constant now, right? It's like partial derivatives. It says, oh, I allow n to change now, H constant. Here, I keep n constant, I allowed H to change, right? So then you say, here's the combined possibility of all possibilities. Okay. Let me recapture you guys if I've lost you. What I'm trying to show you is that if you are transmitting light through an object and that object is physically strained, we are mechanicians, right? We're not optical engineers, but I need to take you down this little road, okay? And it says, let's look for the things that happen in mechanics. We could stress this thing. Maybe its index changes. Maybe there's some relation between the strain this material feels and index. We could account for that, okay? And its thickness could change, okay? So it says we can probe, in principle, objects in transmission that are undergoing some kind of deformation, and something about the interferometer, because it knows how to track phase. And I haven't told you how it does that yet. You have to keep believing that, okay? I'm just trying to show you why would we want to track phase. We want to track phase because it lets us probe deformation of things, okay? This is in transmission, okay? This is in transmission. Now, there are other cases. How about reflection? This is the one that I opened up with, right? Here's reflection. This is if you followed that one, this is even easier, okay? Remember, light travels at 3 × 10⁸ meters per second. It's so much faster than anything you're testing in the laboratory, okay? It's ridiculously faster. So at some instant of time, T1, our surface is here, where the edge of the blue object is, and at some later time, it's there, okay? The laser beam that probed that surface has this little gap that it has just detected. If we continue to monitor, it says, this guy was here, and I reflected some light back when he was here, and now he's here, and I reflected some light back when he's there, and there was a round trip, 1, 2, inside here, associated with this gap, delta. Guys follow that? Okay, so there's a round trip 2 delta, and that's why this 2 just shows up here. And this should be very familiar to us. We just talked about this. This is the optical path associated with one of the deltas. So if this is delta, the optical phase was 2 pi over lambda naught delta. So there was, on the way in, there's this much phase, delta phi 1. Then on the way out, there was another one, right? Plus 2 pi over lambda naught. Okay, delta. Remember, light is just so fast that it can probe these things. And so what you're beginning to see is that, again, if you have a magic device that can somehow probe phase, it would then see that gap change that just occurred, that delta that just occurred between time 1 and time 2. Okay, so that's what interferometers do, and I'm trying to convince you that that's what they measure is phase, but I'm trying to show you why we would care. Why we would care is because, go back to the cantilever that I showed you on the first slide. The surface is moving, right? There are many of these repetitively happening, right? It's doing this to the laser beam, and we're saying we're shooting that laser beam at it and down, and that phase is being recorded, okay? This phase is being recorded continuously, and the gap is changing with time because the beam is decaying in its vibration, right? So we're plotting this somehow internally in the device because the device can track phase, okay? I still haven't shown you how it does that. I have to do it this way first to motivate why we care. Because if I suddenly just went on an escapade and started talking about optical phase, you'd tune me out. So I have to keep reminding you why it matters. It matters because it gives us metrics in mechanics that we care a lot about. Like, wow, we can somehow probe the motion of a surface, okay? Or even the whole surface itself, okay? You could reflect a big laser beam off of an entire surface and bring these interfering beams to a camera instead. And now the camera is seeing the interference field-wise, right? Here, we're imagining just reflecting off a single point like the vibrometer does. So here we'd only be measuring point motion, okay? But the two are open to us in principle, okay? Okay, now, so questions that need to be answered, and we'll answer only so many today, and then we'll finish Friday. How does mixing two beams together, how does doing that, mixing two beams together in this way, produce a signal that we interpret as an optical phase change? Because that's what interferometers do. And then how is this phase change recorded? Like, how do we actually record such a signal? And then how is it then converted to displacement or velocity? Okay, those are the three questions that we're really trying to drive toward. Okay, now I hate this slide, but I have to have it. It's obligatory, because if I don't talk about it in some way, shape, or form, again, we lose an important piece of the story. So I'm going to go back to, you had to have learned your E&M somewhere, probably here, and you had to have heard of the Poynting vector, okay, E cross B, okay? And why Poynting vector is so important is because at the end of the day, what Poynting vector measures is power per unit area, or energy per time per area, okay? Impinging on a surface, optical energy. That's why it's important, okay? Forget the derivation, okay? All this derivation is telling you is that in the end, it turns out to be this cross product between E and B, but oh, by the way, because E and B have this cute relationship, we don't even have to talk about the B field and a light field, okay? There's also a magnetic field, right? There's an E field and an oscillating magnetic field, and they're traveling along. But in the end, we can get rid of the B. So there is something called the Poynting vector. But before I leave this slide, I just want you to understand that it has to do with the energy per unit area that you're impinging on your detector. What's your detector? It's a photodiode, maybe, whose job in light is to just like a single pixel, just gets light and turns into an electrical signal. Or it's many of those on a camera chip, right? And those see this thing called power per unit area being impinged on them. And so when you have to put a mathematical description about how that relates to the fields that make up the light, well, it happens to be that, okay? And the way it's argued is just on this page, okay? A very simple way of arguing that, okay? Now, here's the catch. Please, tune back in if you momentarily tuned out, because this is the magic. This is, I swear to God, before we see the math, just hear this one out. Never forget this. Light fields vibrate at an obscene frequency. Look at that number, okay? It is physically impossible for a detector made by humankind, okay, to follow a 10 to the 14 hertz fluctuation and produce for you an electrical signal of 10 to the 14 hertz, okay? There's no such detector that's that fast, okay? The human eye is like really poor in that sense, okay? And never mind this, anything we make, that is just way too high. So the best any detector can do, any camera, any photo detector, is a time averaged representation of the pointing vector, okay? That is what detectors, cameras, anything sees, is a time averaged result of the pointing vector, okay? Time averaged. And I'm skipping a ton of math between that sentence and that sentence. But here's like one cool thing that I will say that like you benefit from 95A, okay? Is that I'm telling you that the derivation leads you to this amazing recipe, which, you know, if I put that in, everybody'd be like, forget it. This has just become an optics course, okay? But it's a beautiful thing, okay? It says, in the end, the time averaged pointing vector just says this amazing recipe, okay? We forget the proportionality constants, they're not important. It says, if you can represent the E that's made it to that side of the beam splitter that came from the specimen, okay? All right, so if you know how to write somehow mathematically the electric field from the specimen beam plus the mathematical representation of this reference beam that you're mixing it with, 1, 2 on this side, we can call that E, okay? And the time averaged intensity that the detector that receives that will see is given by E times E conjugate. And that gives us a real quantity, okay? This is these guys are complex. You saw it. I showed you the plane wave formula. It was E to the I something, right? And so the amazing derivation says the time average pointing vector says, give me the two E fields that you've just combined, multiply them by their complex conjugate. So really, it ends up becoming ES plus E reference times ES conjugate plus E reference conjugate. And you have to multiply all that out. And you'll see this again. I'm not going to let this go, okay? But I just want you to see the magic. So there's a lot between these two slides that you have to take on faith, and only someone who was really determined to understand interferometry would say, oh, let me go back my one time and see how this pointing vector gets time averaged by devices, and why in the end, all we really report is this EE conjugate. This is intensity. This, like if you mix two laser beams and why you see have you ever seen a stationary fringe pattern before? Okay, I'm going to show you one because I have some links in here. Like you mix two beams and you see this beautiful pattern like this, these fringes, okay? This is bright, and then there's a dark fringe, and then there's this other bright fringe, okay? You're reflecting two beams and mixing them, and you make this pattern that gets developed that the camera could record, okay? All right, and these are called fringes, okay? So this is bright. This one is dark, and there's some variation going on. That is a standing interference pattern, which is the EE conjugate that the camera is seeing, okay? That your eye is seeing if you make that pattern and project it on a sheet of paper in the lab, okay? So I have to tell you this because that's the recipe for how to do the interferometer equation. And we'll do the most general one. Okay, so this is what I've just written on the board. Okay, so what we're doing is we're going to say, okay, our photodetector of our interferometer, our vibrometer, okay, is going to receive two beams mixed appropriately and collinear and concentric. Remember I said that at the beginning? Yeah, they all get aligned so nicely and they superimpose on each other and they have E1 and E2, and we'll just start following the mathematical recipe of the EE conjugate. So you'd have to write that, right? This is just very basic algebra now, and one sentence at a time, you say, what would we get? Let's pause and stare at this for a second. So it says a receiver that receives two interfering laser beams that are superimposed in the manner that I've proposed would see the following. the fringe pattern that you see, okay, or the light signal that is going to a diode, which is being converted to an electrical signal, has this first piece, which is constant. This is E1 conjugate, and this is essentially the intensity that you're seeing has intensity I1, and this is nothing but E1 dot E1 conjugate. Let me state it differently. If I had an interferometer that looked like, let me now draw a very simple rendition of an interferometer, okay? So suppose this was a mirror, and then this was the beam splitter here, okay? And let's see if we can get ourselves to a situation where we can mix two beams, okay? So all right, so suppose we send this laser beam with lambda naught from this laser, and we traverse a path, and we create E reference here with this one, and we bounce this one off of a mirror that will have some motion delta, okay? This one will be allowed to perturb a little bit. These are small displacements, okay? Obviously, if you move this thing too much, this whole thing's going to become out of alignment. Again, we're talking about measuring small things now, right? So this then is E specimen, this beam. It gets perturbed by this moving mirror, okay? And then they mix on this side, and you get, right, E reference plus E specimen, right? And that's the E we're talking about here. And that's what this is telling you. This is saying, now let me do my analogy. Suppose we had this set up in the lab, and we were seeing this fringe pattern projected on a sheet of paper right here. So put a sheet of paper here and a sheet of paper here, and you'd see the fringe patterns projected, okay? Fringe pattern, okay, would be projected on that sheet of paper. It's the mixing of these two beams. Remember, these beams have a spatial dimension to them, right? They have like a diameter d. So, you know, we could even see something spatially like that when we mix them together. And if I would have just put a sheet of paper in front of this beam momentarily, the fringe pattern would disappear, right? It has to disappear, right? Because I blocked the beam. But the detector still gets light, right? It still gets that light from E reference. That's what this I1 is. That's what this is. This says the standing background intensity from beam 1. That's all this is. This one is the standing background intensity from beam 2. Literally, if you were to block, okay? So I block the reference. Now this one goes, okay? So this is just background. We call this the DC portion, DC, because it's not direct current, but people use that acronym for everything, okay? This is your DC light background, okay? The light beams, if they were just like on the sheet of paper without another one superimposed with it. Here's the magic. It's this term right here. It's the combination of these cross products between E1 and E2 conjugate and E2 and E1 conjugate. They are the ones that give rise to this. Okay? The interference that you get from an interferometer comes from these terms, okay? And that's where the magic of interferometry happens, okay? These give rise to interference fringes, okay? That's the summary of everything we just talked about, okay? The photodetector or the camera is here, and if these beams are appropriately interfered and they have some common, again, this is laser light with a single frequency. You try doing this with a flashlight or a white light beam, this is never going to happen, or at least not under controlled conditions. You need laser beams have unbelievably important properties, and one is the monochromaticity, that single wavelength, or nearly so. Number two, I'm not digressing too much into this, but it's the coherence length. Those waves coming out of the laser are incredibly coherent for a very long time, okay? And so you can mix beams, you can have them be separated from each other and recombine them, and they still remember each other phase-wise, okay? White light is being produced by all these atoms jiggling and bumping into each other. The coherence of white light, the coherence length of white light is on the order of nanometers, okay? So if you were to make a white light interferometer, the path length difference between these would have to be on the order of nanometers for you to possibly even hope to make a white light interferometer. And by the way, it is done. It is done, and that's another chapter for another day, okay? But lasers give you this flexibility. Their wave train have these long coherence lengths, could be meters, okay? And so you can differ these path lengths and not worry that these beams won't remember each other phase-wise. Question? Yeah. They would see two signals that are pi out of phase. I just didn't want to get into it yet. Okay, so where one has a dark fringe, the other would have a bright fringe. And that's actually very useful sometimes in data reduction. Okay, so because of conservation of energy, that's the easy way to answer it. If you apply conservation of energy, that's why the two have this pi phase difference. But easy to say, you'd have to. No, that won't change. Their spatial size will change as you move the sheet of paper, maybe if they're diverging beams. But the intensity patterns remain preserved. Okay, so here's my plans. I've got 2 demos for this. I'm driving to Irvine today. I'm leaving after I meet with TAs after this meeting, and Polytech, the people who make that vibrometer I showed on page 1, they lend that to me every year for free. I've had a long-standing friendship relationship with them, and they just let me keep it for months if I want it. Okay. And I'm going to bring it back and I'm going to do some demos with it. So we're actually going to use that device. Okay. And it's just a trip to Irvine and back. It's more than worth it. And then that's the small price to pay to be able to get this thing for nothing. Okay. It's tens of thousands of dollars to buy an instrument like that. Okay. And we don't have that kind of extra money lying around to buy that. So that's one. And then 2, you guys might remember the black curtain that you see when you come into the lab that blocks this laser table. So I have some open beam optics that I want to set up so that we'll make one that we can physically see instead of looking at the black box. And then we'll see these pieces of paper and fringes just like you've just talked about, okay? And just be a demonstration, okay? All right, so let me, I've only got a few minutes left. Let me say a few more good words about this. Now, if you then say, okay, we need to now examine, so now I hope I've convinced you that this is the important terms, okay? So now we need to see what's in those, okay? I don't think it's very convincing yet that these 2 terms give rise to those fringes just yet, okay? But let's kind of go to the next page and see what happens. When you decide to say, okay, let's be more specific, okay? Let's not just call them E1 and E1 conjugate anymore. Let's actually write what their plane wave descriptions are. Remember, we digressed into this at the very beginning. So we just go back and we very properly just say, okay, I'm going to call E1, okay? I hat means it's oscillating with its E vector in the I direction, okay? And there's some amplitude, E to the I, K dot R minus omega T, but now we add a little arbitrary phase term because they can, in fact, have arbitrary phase terms associated with the fact that they've traversed different distances, okay? So that's an accumulation of phase. So we just say, hey, let's have a placeholder for arbitrary phase that this beam could have accumulated versus the other one, okay? And the other one would have a phi 2 in its place, okay? That's the only difference between, oh, by the way, and I'm purposely putting this one as M hat because I want to remind you that this is a dot product. And it's very interesting. I don't think it's on the board, so I think it's best to go back. And I didn't say this, but when you do this, this is actually representing a dot product. And you guys know the dot product of 2 perpendicular vectors is 0. You see? So that says if you try to mix 2 beams of light, one of which has an E field that's doing this, okay? And the other one which has an E field 90 degrees away, they don't interfere. You get nothing, okay? Because its dot products go to 0, okay? So I'm building that M hat into that new page on purpose, just to say, okay, we'll allow this one to have a slightly different orientation, But man, these better never be 90 degrees out because then they're going to go to 0. Okay. All right. So then you just write their conjugates here, right? Notice the minus that I'm putting here. That's all. A minus there and a minus there. I mean, just set it up for the recipe, right? We need themselves and their conjugates. Okay. I will now just cut to the chase and tell you this is the magic answer that you get. And it comes from your knowledge of Euler's theorem, from things you saw in Math 2 and 95A. Euler's theorem gets invoked at some point because we recognize that we have e to the I something plus e to the minus of the something. You see it? Okay. And we say, oh, that's a recognizable thing. Okay. If we just divide by 2 and multiply by 2, that's cosine, right? See, so doing the complex analysis, following the recipe, leads us to this magic place that says, the interference term has e to the I this difference plus e to the minus I that difference, okay? And we say, oh, great, we get to call that cosine. So now for the first time, even though we're out of time, let me just leave you with this thought. It says your two interfering beams have a stationary background intensity 1, right? That lonely intensity of that beam if I block the other, right? And the I2, they are just background. Then fluctuations happen spatially, okay, or temporally if we're sitting at one point, because the argument of this cosine function could possibly change in your experiment, you see? And what's in the argument of this cosine function is this phi1 and phi2, which says, oh, those get accumulated by path length changes between the two. And so if their path lengths are differing, this starts to change, the argument changes, the cosine changes, and this thing starts going up and down. You see? And that's what you're capturing. And then I will unwrap for you in 2 cases. Like we'll look at the possibility that this might contribute or that or both contribute. Okay. And that we'll do next time. Okay.